Hello everyone. Today's lecture is on design of experiment, or in short DOE, which is an important topic when it comes to knowing how to conduct an experiment. Well, but first, what is an experiment? Experiment is a systematic procedure which we do under some controlled conditions, maybe to discover an unknown effect, or maybe to test a hypothesis, or maybe we are interested in knowing the effect of some inputs on outputs. Well, a good experiment must be simple, cost-effective, and of course repeatable. And keep in mind here, when we refer to design of an experiment, we are not referring to how to design the apparatus or tools or the sensors. Is more on how to conduct a test and change the parameters in a cost-effective and efficient way. So then DOE answers these three questions. Which factors we need to test? And factors here it means parameters. And then at which levels? How should we change these parameters? Let's say if we are doing an experiment that it involves time and temperature, how should we change these parameters, the steps that we need to change the parameters, and also the structure of changing these parameters. Well, when it comes to structures, if the experiment involves only in one single factor, then it's not that complicated. We may change that single factor step by step and we will see the effect. Either we increase or decrease it to see the effect. But it is a little bit more complicated when we have multiple factors. There are two approaches. One is to keep everything constant and change one parameters at a time. And the second approach is factorial design, which is the focus of today's topic. So the objective of our lecture today is, first of all, to know the concept of DOE and some terminologies related to that. And by the end of today's lecture, you should be able to conduct a two-level factorial DOE. You form the table and then do some basic analysis with DOE. Hopefully, you can use this information maybe in your capstone experiment, or maybe for future if you are doing some real-world experiment. Keep in mind, DOE is a very large topic, and there are in fact courses with the title of DOE. If you are interested, you can look them up and you can register in those courses. So the whole course dedicated to the topic of DOE. But in this short lecture, we're going to only focus on what we need, like the very basic, and it's good enough to conduct again an experiment and analyze the data. And there are softwares and programs as well. For example, MATLAB or Python, they do DOE, and there are software specifically for DOE, but we don't use them, and also we don't use Python and MATLAB. Here again, we want to know the concept and how to form a DOE table. So with that, let's get into it. Single factor, the very basic experimental test. It involves only one parameter. We need to test only one parameter. A good example from last lecture is the strength of toilet paper as a function of the hardwood concentration. So you saw in that example, we were interested in knowing if the amount of hardwood has an effect on the strength. So what we did, simply at each level, and again level here means like 5%, 10%, 15 and 20% of concentration for the amount of hardwood, we conduct a test, and of course, we repeat the test, like here you see 5 or 6 times, and then we will do an ANOVA to analyze this data and to check the effect of the amount of hardwood, or to see if the amount of hardwood concentration has any effect. So this is what we discussed last lecture. Then let's move on to the multiple factors. So there are many examples in engineering that involves testing more than one factor, right? Let's look at this example that I did as a work when I used to work in a car manufacturer. For a passenger car, dynamics, and here by dynamics it means the ride and handling of a car. Ride means the level of comfort, so we want the minimum amount of vibration to transfer to a passenger or to the driver. And dynamics again can refer to handling. At the same time, we want the car to be stable. So if we do a maneuver or we are turning a sharp turn, we don't want the car to go unstable and flip over. So there are many parameters when it comes to designing the chassis of a passenger car. Complex geometry, or the parameters such as this, the stiffness of the springs, the damping ratio. There are many joints and bushes, like they are flexible bushes, like the one that I showed here by X1 and X2 and X5. So total maybe 10-15 parameters that we need to test. And usually the test of these parameters, if we change something, first we do a test on a test rig, which we simulate a road, like similar to the picture that you see on the right, and then we take the car on a road. We attach some sensors, as you can see here on the car, to test various parameters. So imagine conducting a test for a car, which again is very expensive, and wanting to change these parameters. How should we change? Let's say we have 5 parameters here, the one that I showed here in this middle picture. And how should we design this experiment? Should we keep all the parameter constant and change only one to see its effect? Or maybe we should change all of them altogether. Then how should we change them? Should we increase all at once, or decrease all at once, or increase some parameters, decrease some other parameters? This is the question that we would like DOE tells us. What is an effective way to design this experiment? So approach number one factor at a time. What does it mean? It, as the name implies, keep everything constant and change only one parameter. Let's look at one example and see how this method works. Let's suppose that we have a chemical process, whatever. And suppose that this chemical process is being influenced by 2 factors, temperature and time. All right, 2 parameters influencing these chemical process and the yield material of this process, whatever it is. Currently, this process is being done at temperature 346 Kelvin and time 1.5 seconds, the process time. Suppose that this is the theoretical graph of this process. X-axis shows the temperature and y-axis shows the time. And this is, of course, a 3D graph, which here in a 2D picture, we show the slices of this graph. If you want, you may visualize this graph as more like a hill shape, right? Which we are on the hillside at this moment. We are at this red dot, temperature 346 Kelvin and time 1.5 seconds. So we are hoping to maximize the amount of yield. So we are looking after finding the correct temperature. So right now, at this temperature, the yield is approximately 63%. And keep in mind, we don't have this information, right? If we do, then that would be great. We knew that the best temperature is 344 and the best time is 0.16, like this star at the top of this hill. But we don't know. So you can imagine that we have this graph, right? And we don't have any map to get from this red dot to this star, and we don't even know where is this star. Okay, so that's something that you need to keep in mind. We don't have any of this information. We are just, you can imagine that you are on a hillside and you are blind, and by just trial and error you want to get to the top of the hill. So you may go one step to the left, one step to the right, and see if you are getting your level is going higher or higher. So how should we do the test with one factor at a time? So again, if we knew, we straight go to the top, but we don't have this information. Let's get back to this, but we will keep this map, right, to see what's happening, all right? So one factor at a time. Let's keep time constant. We keep the time to stay at 1.5, and we just change the temperature. Intuitively, we may think that increasing temperature helps. So we increase temperature, we get to that purple point on this graph. All right. So we will do the test, and we notice that the yield decrease. Originally, we were 63, but after we do the test, maybe we get a number of 59. Okay. So then we decide that increasing temperature is not a good idea. We decrease the temperature. So good news, the yield amount of the material increased. We are happy, we increase the temperature more. We keep increasing the temperature until we get to a plateau. We realize that increasing temperature more than this is either stay the same the amount of yielding or maybe decrease. So we decide that this number is the best temperature and to gives us the maximum amount of material, yielding material. Now we keep temperature constant and we increase time. So, we increase time. Then we realize that, well, no, not a good news. The yield decreased. Look at this graph. Again, keep in mind, this is only us. We know this information, but the engineer has to do the test. He did the test and he realized that the yield decreased. He is going down the hill, right? So, he increased the time, not temperature, time, and he realized that, well, the amount of material is decreasing. He's going down the hill. So let's get back here. He decreased the time. Good news, the yield is increasing. Increasing the time more, decreasing the time more, keep decreasing the time, and keep decreasing until we get to the point that we realize decreasing more than that is not going to give us any more yielding material. And we realize this red star is the point that everybody is going to be happy, and that's the maximum yield or the optimum point. So we conclude that then temperature of 329 and time 0.5 second is the optimum point with a yielding of 69%. However, this is not true, right? Because we didn't get to the top of the hill. And of course, we don't know that there is a top of a hill, right? Because we don't have any of this information. We just did several tests, and maybe these tests, they were expensive. We had to, or time consuming. We did several tests to get to this point. So our conclusion then is maybe one factor at a time is not really a good approach. Then Let's switch to another approach, second approach, which is factorial design. And factorial design means we change everything simultaneously. Let's analyze the same example. Now we know what is the story, right? This time, but we want to change T temperature and T time simultaneously. So this is how we are going to proceed. We are going to decide for a step or level on how to change temperature and time. Maybe 5 degree or 10 degree, doesn't matter, okay? As long as we know the change is not huge that it results in a nonlinear behavior. So we usually stay with a small change or a small step. So level then means the amount that, or each step that we are gonna take to move on this hillside, okay? So we are going to use some signs, and if we use a plus sign, it means that a step is increasing. For example, temperature, if it's currently is 346, when I'm using a plus sign and I decide a level of 5, it means my next temperature is 351, right? So 346 plus 5. 5 is the level. And minus means decreasing. We have 2 parameters. Then there are 4 possible scenarios. Let's take a look at this table with these 4 possible scenarios. Scenario number 1 is that we increase both. We increase temperature and we increase time. Scenario number 2, we increase temperature but we decrease time, and so on. Scenario number 4, we decrease both of these parameters. If I want to show them on this graph, these 4 purple points, right? Test 1, you can see the temperature increased, the time increased, and test 4, we decrease both. Look at these 4 tests. Again, we have this information, we have these graphs, but the engineer, he doesn't, right? For us that we have this information, we have this graph, immediately we realize that what is the best scenario or what is the best test? It's test 4, right? Because test 1 obviously results in decreasing the amount of material, yielding material. Test 2 and 3 result in maybe no change or little change or maybe decrease. But test 4 obviously is moving toward the higher level on the hill, right? But engineer, he doesn't have this information. He has to do these 4 tests, and let's assume that he did the test and this is the value that he got. Look at these numbers. If we look at these numbers, we realize that 66 is bigger than the rest, and obviously minus is the best approach, or test 4. So doing this test, like these 4 tests, he immediately realized that decreasing both parameters simultaneously result in higher yielding, and you'll see in just one shot he got to 66. But let's be patient. He can do more with this data. He can add these values using this sign that we have here. Take a look at T, temperature. I'm adding these values using these signs here. Like you will see 59 plus 63 minus 61 and minus 66. It gives me minus 5. I repeat the same with time. I get to minus 9. So I have 2 numbers here, minus 5 and minus 9. These 2 numbers gives me very good information. They tell me that between these 2 parameters, temperature and time has a higher effect on the output. Its effect is almost twice. A negative sign tells me that decreasing these values because they are negative, result in better or they result in an optimum yielding material. In other words, if I decrease these values, because I have the -5 and -9, the minus sign, I'm just focusing on the sign. Because of the minus, we realized if we decrease these, then we will get to a higher result. And also it tells me if between these two parameters, time is has a more influence. And if I want to change just one parameter, maybe because of limitation, maybe I should focus only on time. And obviously from this graph you will see, even if we keep the temperature constant, let's say you are on this red dot and you keep the temperature constant and you just work on time, you will see you come down on this straight line and you will get very, very close to the top of the hill. Okay, so then let's summarize. In a factorial design, we change parameters simultaneously. We decide for a level the steps that we need to increase or decrease, and we form this table, and this is a table with this plus and minus sign. It's called a DOE table. We conduct a test at each test or treatment. We can call them treatment. Like test 1 is treatment 1, which temperature increase, time increase. Test 2 is treatment 2, plus minus. Okay, and then we will add or subtract these numbers to realize how should we change these numbers and which one has a higher effect. Again, keep in mind, DOE doesn't tell us how much we should change them to get to the optimum point. That's a different topic related to DOE, but totally different topic. DOE tells us what is the direction of change and which factor or parameter has the highest influence on the system. Okay, let's solve one example, and hopefully through this example you can understand this concept better. I'll let you guys to read this example, and I will do the same. Maybe while I'm drinking a little coffee, I need a little bit of energy. Well, we have a lathe machine, right? And when we do a machining with a lathe machine, surface quality is important, and a good measure is surface roughness. And for now, let's not focus how we can measure surface roughness, but knowing the knowledge of or having the knowledge of machining, there are 3 parameters that influence surface quality. One is the feed rate, how fast we do the machining; the depth of cut, how much we cut, 1 millimeter, 2 millimeters, or if it is in inch, what is the depth of cut; and the tool that we use and its angle. One important parameters in a tool when we do machining is rake angle. If I show them schematically here, you will see here the parameter that involves in these tests. One is the feed rate, how fast we move tool to the left to do the machining. And the second parameter is D, is the depth of cut. You will see the D over here, right? Of course, the bigger D, it means we can faster remove more material, but maybe it has an effect on the surface. And the rake angle, the tool rake angle, it's difficult to show it on this picture, but you can visualize the angle of this tool with respect to the normal to the surface of the cut, surface of the cut, like this small ring here. Okay, so the parameters here, anyway, the angle of this tool, which we call it a rake angle. And what about N? Maybe they have done the test and they realize that N, the rotation speed, has no effect, or maybe it has an effect, but it is just a fixed number and they cannot change it. Okay, so this is the problem that we have. Currently, they are doing this machining at these three values: the feed speed of 25, the depth of cut of 0.035 inches, and the rake angle of 20 degrees. This is the current parameters. We are interested to see if these values are optimum, or we should increase or decrease them to have a better surface roughness. So our goal here in this example is to form a DOE matrix with two levels. And when we say two levels, it means that, similar to the previous example, we increase or decrease, like a low value or high value. Let's look at the feed rate. Currently, our feed rate is 25 inches per minute. So we decide for -5, so we get to 20, and +5, so we get to 30 inch per minute. All right, so our lower level for feed is 20 and higher level is 30. Okay, and this step doesn't have to be equal. For example, my low level could be 20, my high level could go to maybe 32. But for simplicity, for now, we'll keep them the same. And the same for D low and D high, the depth of cut. So you will see currently we are at 35 thousandths of an inch, and we decided for low to be 25 thousandths of inch, and high to be 40 thousandths of an inch. And again, you notice here that the minus sign and plus level, they are not the same, so that's okay. And the same for alpha. Currently we are in 20 degree, 15 and 25, the same. We keep it the same. So only for D, the increase and decrease are not the same. With that, let's use some signs. So then, rather than writing these numbers every time that we talk about them, let's just have this agreement that whenever I'm referring to minus sign, I mean 20 for F, and for D I mean 0.25, and for alpha I mean 15. And when I'm using a plus sign for F, I mean 30, and the same for D and alpha. Okay? With that, we form our DOE table. First of all, what is the number of possible scenarios? So we have three parameters, F, D, and alpha, and each can have two possible levels, low, high. So the number of then possible treatments is 2 to the power of 3. So I call them test 1 to 8, but some people call them treatment 1 to 8. That's the same. We form our table, and if you are wondering how we realize for these plus and minus, it's very easy. If it's not intuitive for you how to form these and not forgetting each of them, one way that I do it, if I have 8 possible scenarios, for the first parameter, I decide to change the sign every 4 steps. Right? So I have 8 total possible scenarios, divided by 2 gives me 4. So for the first 4 positive, and then the next 4 negative. Then the next parameter, I change the sign every 2 steps. So plus plus, and then minus minus, and so on. And then the last one, I change it every after each step, like plus minus, and so on. Okay, and it doesn't matter which parameter is first, which parameter is second. If we look at this, we have all the possible scenarios. We have, for example, scenario number 1, which all of them are positive. Scenario number 8, which all of them are negative. Scenario number 2, the first 2 are positive, and the alpha is negative, and so on. And again, it doesn't matter which parameter is first, which is second. So we have 8 possible scenarios. Let's say we've done the test 8 times, and we repeat each test 3 times. Okay, repeating a test is important because we may do some mistakes. So minimum 3 times, but of course the more repeat the better. But again, of course, it depends how costly or expensive the test is. So we decide to repeat each test 3 times. Okay, this is the table that we have. We finish with our test. We've done the test 24 times, right? For each for each treatment, test 1 to test 8, we repeat them 3 times. We have 24 values. Our test has been done. Now it's time to analyze this data. First step is to make sure that there is a significant difference between each treatment. Maybe these changes is just due to the chance, right? How we can analyze this data to find out that there is a significant difference between them, or in other words, how can we test this hypothesis that there is a significant difference between these 8 groups? Well, we formed our null hypothesis. Our null hypothesis is saying that no, all these 8 groups, they are coming from populations with the same mean. So mu1 is equal to mu2 to mu8. And if you can see any change here with these numbers, it's just due to chance. Okay, this is the null hypothesis, and we want to test it to see if it is true or not. Well, from last lecture, you know, we have 8 groups, so we have to do an F test. So K is 8, and N total, the number of tests, is 8 multiplied by 3. And let's do a test with a significant level, or alpha 5%. So please follow the procedure. I didn't show the calculation here, but the same procedure as last lecture, lecture 10. We will find the variance between the groups, between these 8 groups, and the variance within each groups, and we'll get to this large number. Obviously, looking at these values just visually, you may get to the same conclusion that the variance within each group is very small. Look at treatment 1, 15, 16, 14. Look at, for example, treatment 7, 10, 10, 11, or each of other one. You will realize the variance within each treatment is very small. It's maybe in a range of 1. It's very small. But the variance between groups is large. Like treatment 1, the range of values is around 15, 16, but look at treatment 8 is 8, 9, 7. Large variance between them. Anyway, we have a systematic way to calculate these values, and we find our test statistic F, which is 12.34. We compare it with a critical value. We look up our F table, and based on DF1, degree of freedom 7, which is K, 8 minus 1, and DF2, which is N minus K, 24 minus 8 gives me 16, and alpha is 5%, and our critical value is 2.65. Obviously, 12 is way larger than 265, and we realize that we are in a reject tail region, and so we reject our null hypothesis. If we reject our null hypothesis, it means that there is a significant difference between these 8 groups or 8 treatments, and it means that these parameters F, D, and alpha has a significant effect on the output, which here is the surface roughness. So what is next? Well, now that we know there is a significant difference, we need to find out which of these parameters has the most influence on an output. And to do so, first of all, we work with the mean. We calculate the mean of these 3 numbers. Here are the means, and I round them a little bit for those that I don't get a round number. Just again, for simplicity, working with this data. But in an actual test or in your exam, we expect you to keep the digit maybe up to 2 points after decimal point. So as I explained in previous example, now we add or subtract these numbers using these signs that we have here. For example, how did I get this value 13 here? Well, I add 15 plus 13 plus 11 plus 11 again, minus 9, minus 10, minus 10, and minus 8. I'm using this sign, right? And I get to 13. I repeat the same for D, and I repeat the same for alpha. Well, looking at these three numbers, now we realize that, first of all, these three numbers, they are all positive, okay? So our first conclusion is that increasing these numbers result in higher values for surface roughness, for output, okay? But we don't want higher surface roughness, right? DOE doesn't care what is your output. It tells you how you should move or change each parameter to get to the higher number. So looking at these values, we realize that, well, if I want a better surface roughness, I should decrease these numbers, okay? Because right now my DOE is telling me that if you increase these values, you will get to the higher numbers. The second conclusion that I can get is feed rate, F, has the highest influence, right? It is almost twice as the depth of cut, its effect. And the effect of D is almost twice as the effect of alpha. So if I want to just change one parameter, maybe I need only to focus on feed rate. For example, if I decrease my feed rate without changing any other two parameters, then I will end up with a better surface quality. So let's summarize what we had. We conduct an experiment to test a hypothesis and to check the effect of an unknown parameters. DOE is a systematic way that tells us which factors need to be tested and which factor is more efficient. It provides a procedure, let's put it that way. It gives us a table of a test. How should we change the parameters in a or combination of parameters? And we studied in this lecture a two-level factorial test. So in total, we have 2 to the power of k combination. K is the number of parameters that we have. And we use plus and minus sign to show the higher or lower level. Each treatment should be repeated several times, similar to the example of the machining that you just saw. The engineer repeat the test 3 times, at least 3 times, but the more the better. So we'll do an F test first of all, to check if there is any significant difference between each treatment. That's before doing anything. And then we will use the mean value or the average value of the test for each treatment. Remember, we repeat the test several times. We will use the average, and then we will use the plus and minus sign from the DOE table to calculate the degree of the effect on the result, and finding out which parameter has the highest effect. Well, with this summary, we finish the topic of DOE, and please study the material that has been posted on Canvas, and let me know if you have any question during one of the live lectures. Thank you and have a great day.